Hello, my name is Cody Abrupta, and I'm a licensed professional civil engineer working for the Maine Department of Environmental Protection. I'm a member of the Stormwater Engineering team, which is part of the Land Bureau. Today, we're going to be talking about vegetated soil filters. Here's an overview of how the presentation will go. We're going to start talking about the function and design of vegetated soil filters. We'll then talk about infiltration and the associated requirements. After that, we'll go through the construction process, and then we'll talk about inspection and maintenance procedures, as well as the 5-year recertification requirements. So what is a vegetated soil filter? Well, it's a stormwater best management practice that consists of a shallow depression in the ground that collects and provides quality treatment for stormwater runoff. Vegetated soil filters can have a variety of different types of vegetation. You can have native plantings, which can include trees, shrubs, bushes, wildflowers, and grasses, or the system can be left grassed, in which case it's often referred to as a grassed underdrain soil filter, or a GUSF. How do these systems function? Well, they provide physical filtering. So, stormwater runoff often has a lot of floatables, whether it's trash, litter, debris, or sediment. Those particles or those floatables are not allowed to pass through the void spaces in the soil, and so they're basically filtered out of the stormwater and deposited on the surface to be removed later by routine maintenance. These systems also provide nutrient uptake, and so nitrogen and phosphorus that are in the stormwater get effectively removed to some degree by the vegetation, the root structures, and then also the soil microorganisms. There's also some additional chemical breakdown that occurs in these systems, and they provide another function, which is the slowing of stormwater runoff. Again, one of the goals with stormwater management is reduction in peak flows in the post-development condition compared to the pre-development condition. When you're putting in a lot of impervious area, it drains really quickly. And so these systems are effective at slowing down that stormwater runoff because it takes time for the stormwater to pond and travel through the soil layer. Now you can see from this image, this shows two different options. Sometimes these systems are designed as infiltration systems, which means stormwater enters the basin, it ponds on the surface, and then it slowly travels through the soil bed. If it's an infiltration system, it's allowed to infiltrate into the existing soils on the site, or the native soils. If the system is designed not to infiltrate, it often includes an impermeable liner or a clay liner to prevent water from entering the native soils. It also then typically includes an underdrain system. Basically, you have a gravel bed where water that infiltrates through that surface filter layer ends up in the gravel bed. From there, it enters the underdrain, which is perforated, and then it leaves the system. These systems often have an outlet structure, and they almost always have some type of emergency spillway or overflow spillway. Both of these are included for larger storm events. So let's talk about underdrain soil filter and vegetated soil filter design. First, these systems need to be designed to detain runoff volume equivalent to 1 inch of the subcatchment impervious area and 4 inches of the subcatchment landscaped area. And so basically, your impervious area, you multiply that by 1 inch, and that's how much rainwater you need to capture. If you've got landscaped area, you multiply it by 0.4 inches, and that's the volume of stormwater runoff you need to capture from those areas. The filter surface area needs to be at least 5% of the contributing impervious drainage area. This is just to get the sizing correct. And the filter area should not exceed 3,000 square feet or have a larger than 2.5 acre drainage area. These are according to Chapter 7.1 in the Stormwater BMP Manual, Volume 3. And then also, these systems should be designed with a stable overflow outlet that's provided for any volumes that are in excess of the treatment design volume. You can see from the detail in the plan view, this is what the system might look like as a detail. You can see that the system has either a geotextile fabric lining if it's allowed to infiltrate, or an impermeable liner at the sides and the bottom of the system. Um, there's your underdrain with a gravel layer, gravel reservoir. You can see in the detail on the left side, this system has a choker course or a pea gravel layer to help prevent the soil filter from ending up in the gravel reservoir. You have 18 inches of your soil filter bed, and then above that is your channel protection storage volume. These systems are also sometimes designed to store additional volumes of water associated with the flooding standard. The image on the right, or the detail on the right, shows a bird's eye view, a plan view of the system. You've got your inlet, which is sometimes a pipe, sometimes it's just direct entry, or from a ditch system. In this example, there's a sediment forebay. Sometimes pre-treatment is included prior to this management practice. Sometimes it's included as part of the management practice in the form of a forebay. In this plan view, you can also see the underdrain collection system. You can see the emergency spillway. This specific example doesn't have an outlet structure. It just has the underdrain pipe leaving the system to a stabilized outfall area. Some other design requirements or additional design requirements: these systems need to be designed to drain between 24 and 48 hours after a storm event. The reasoning why we don't want it draining before 24 hours is because we want good contact time with the soils to ensure that there's enough treatment, enough nutrient removal. We don't want it taking longer than 48 hours to drain, because then you have some problems associated with mosquitoes, and it could impact the function of the system. Now, you can accomplish drain time in a couple of different ways. Often we see orifice sizing calculations. So basically there's a cap that's put on the end of the underdrain, and in that cap there's a hole that's drilled, and that hole will control how long it takes that entire system to drain. And so you can size the system, you can size that orifice to ensure that it drains in that window. Oftentimes too, we see these systems installed with a valve that can be opened and closed. If it's installed with a valve, you also need to include a setting procedure. So for example, once the system is built, the valve is closed, the system is allowed to fill up either naturally or filled up with water intentionally, and then the valve is opened or the valve is set in such a way that the system will drain between that 24 to 48 hour window. That may require the guess and check method. We can also model the drain down time with other modeling sources. There's a number of different ways to do that. And then finally, one of the other really important design requirements is you need to submit a detailed log of a soil test pit in the area of treatment that extends 3 feet below the lowest component. Now, soil test pits are really important, especially for infiltration systems, as we'll talk about later. But also we want to make sure that we're establishing where the seasonal high groundwater table is, if it's located, at an elevation that's relevant to the system. We're also looking for ledge, right? The presence of ledge may require blasting for the system, or it may require you to move the system elsewhere. If the groundwater is high, you may need a dewatering plan. And so the only way that we're going to find out these details is with a soil test pit. So I mentioned infiltration before. We'll talk a little bit about some of the considerations for infiltration. So infiltration isn't something that's prescribed everywhere, and it's not every vegetated soil filter system is an infiltration system. Areas where we definitely want to avoid infiltration systems are areas that are contaminated, or brownfield sites, VRAP sites. Those areas we don't want to infiltrate. It also is highly dependent on the drainage area use. So for example, a high-use parking area, a high-use roadway, an industrial center, a gas station. All of these areas have higher surface runoff pollutant loads, and so we would either require a lot more pre-treatment before considering infiltration, or we may not require infiltration on these sites at all. Another factor is the seasonal high groundwater table. There's a mandatory separation distance I'll discuss in the next slide. That's basically to ensure that your groundwater mounding doesn't enter the basin. So if you look at the image on the right, when it rains, water enters the system and it infiltrates into the ground. Well, that actually creates a temporary groundwater mound over the seasonal high groundwater table or over the groundwater table. And we want to make sure that there's enough distance between the bottom of the bed and the groundwater that you can have that mound effective, where the stormwater is still getting treated by those soil layers. And again, seasonal high groundwater table is determined by those test pits, which I mentioned in the last slide. And then finally, we want to know the soil makeup. If the soil area is in a karst area which has a lot of limestone, we would not want to put infiltration there because it could create sinkhole issues. Additionally, we want to identify the hydrologic soil group, so that way we know what the anticipated drain time is, and we can design the system to infiltrate. We can design the system large enough to infiltrate the water. Here are some additional design requirements associated with infiltration. So the sizing requirements are the same as the standard vegetated soil filters that don't include infiltration. One of the important details is the permeability rate should be no greater than 2.41 inches per hour. The reasoning behind that is if the system infiltrates too quickly, you may not be achieving the same nutrient removal, pollutant removal that you would see in a slower draining system. You need to have 3 feet of separation from the seasonal high groundwater table, like I mentioned earlier. And you need to include observation wells, a staff gauge, a marked rod, or some other method to measure sediment accumulation and measure drain time. These are just ways to ensure that the system is functioning as designed. And you can see the cross-section on the right side is for a typical infiltration basin. You can see your inflow, some type of energy dispersion structure, which is usually riprap. In this case, this system has a sediment forebay. Like I said, with infiltration, we want to ensure that we're getting adequate pre-treatment. And then the system doesn't have a soil filter per se. It's using the native soils as the filter. And the separation from the groundwater is shown on this cross-section, as well as the emergency spillway. For more information, additional requirements, and design guidance, you should see Chapter 500, Appendix D, and Chapter 6 in the BMP Manual, Volume 3. So let's talk a little bit about the construction process for a vegetated soil filter. It starts with site preparation. So this includes clearing, installing your erosion controls and sedimentation controls, stumping, grubbing, etc. And then from there starts the excavation. So the system is excavated, you dig your pit. There's also associated grading activities. Sometimes these systems are designed as temporary sediment basins before they're converted into a vegetated soil filter. If that's the case, you need to refer to the design guidance provided by your engineer. Once the system is excavated, the liner is installed. Again, not all systems have a liner. If they don't include a liner of any type, then they're infiltration systems. Any system that's not infiltration will include an impermeable liner, a clay liner, or the native soils will be sufficient to prevent infiltration. Once the liner is installed, if that's applicable, then the underdrain system is put in along with the stone bedding. Again, this is specific to systems that include an underdrain. Not all vegetated soil filters, particularly infiltration basins, will typically not have an underdrain system. But if there is an underdrain system, the stone bedding is installed, the underdrain's put in, and then at this point, if there's an outlet structure, the outlet structure is often also installed and connected to that underdrain system. From there, there's a pea stone gravel layer or choker course. Not all designs have this. Be sure to refer to your details. But again, that's to prevent the soil filter from migrating into that gravel reservoir. After the choker course is put down, that's when the soil filter is installed, along with any inlet structures. The forebay is typically installed at that point. The emergency spillway is lined with riprap. And then from there, the vegetation is established, whether it's loamed and seeded. Sometimes these systems are planted. Sometimes these systems are mulched to help promote growth in those early stages. And then from there, you're continuing with post-construction inspection and maintenance procedures. And so that is the construction timeline or the construction process for these systems. Maintenance plan for vegetated filters. An inspection and maintenance plan should be included for the pre-treatment measures associated with the system, the filter embankments, the vegetation, the underdrain piping, and the overflow spillway. A maintenance plan should include provisions for sediment removal and disposal, rehabilitation of clogged surface linings, and flushing of the underdrain piping if the system contains an underdrain system. Here's an example of a underdrain soil filter, and then I'll walk through what a typical inspection might look like. Again, inspections can happen at different times. These systems should be inspected at least once annually, but typically we want to see them inspected in the spring and fall or after major storm events. The inspection and maintenance activities, let me talk about the maintenance activities first. So typical maintenance activities would be cleaning the basin of debris, trash, litter, sediment, hydrocarbons, etc. So looking in the actual basin and removing anything that shouldn't be there. This can also include weeding if you have particular plantings that are supposed to be in the basin. We're also removing and disposing of accumulated sediments, whether they're accumulated in the forebay or on the basin bottom, near or around the outlet structure, trash rack, etc. All that stuff should be removed and disposed of properly. One potential maintenance activity would be renewing the basin media if the system is failing to drain within 72 hours after a rain event. If your system is taking a really, really long time to drain, that might be an indicator that the system is not functioning properly, and you may need to renew the basin media or remove accumulated sediment. You may need to till, seed, mulch the basin if there are areas with sparse vegetation, and you may need to repair riprap anywhere where underlying filter fabric or the liners are exposed. If the system has an outlet structure, you may need to repair anything associated with the outlet structure that degrades over time, or if the trash rack gets filled up. These are some typical maintenance activities. And then if the system is just a grass system, you might also be mowing the system once or twice annually. Going through the inspection procedure, a typical inspection of a system like the one shown here, this is an infiltration system, but if it's an underdrain soil system, if it's an underdrain soil filter, the inspection is pretty similar. So basically, I would start by looking at the upstream stormwater infrastructure. So if there's any pipes, grass swales, catch basins, I would inspect all of that stuff first, just to make sure it's all in good working condition. From there, take a look at the inlet structures. If there's a pipe or a swale leading into the system, you want to make sure that that's all in good working order. If the system has a forebay or some other pre-treatment measures, you're going to want to inspect that, ensure that there's adequate sediment storage and removing sediment if needed. From there, you check the bed of the basin. So if it's an infiltration basin, you might look into those monitoring wells, or you might check that stuff out to make sure that the system is actually draining properly, there's not too much sediment accumulation. If the system has an underdrain, you may open the underdrain inspection ports, or you may flush the system, the underdrain system, to make sure that there's no clogging issues. If the system has an outlet structure, you're going to want to look at the outlet structure to make sure that if it has a trash rack, it's not totally clogged with debris. That the structure is in good working condition. You'll also want to check the emergency spillway to ensure that that's in good working condition. You don't want any woody vegetation on top of your emergency spillway that could compromise the structure. And then you should also look at the berms or the embankments of the system as a whole to make sure that they're structurally sound. And then finally, the last part of my inspection would include chasing the outlet pipe or chasing the underdrain to where it daylights. Where it's draining the water to the outfall area, you want to just make sure that the system is draining properly. There's no issues with the pipe, no root intrusion, that the area that it's discharging to is effectively stabilized. Those are kind of the things that I would include in my inspection. Any inspection of these systems should also include lots of photographs. It's very important to include photographs in your inspection reports, especially for the 5-year recertification, which we'll discuss in the next slide. So inspection, maintenance, and 5-year recertification. Like I said, any of your inspections, maintenance, corrective actions, they should all be documented and kept in a log or a report. So that way the history of the system is maintained. For 5-year recertification, again, this is specific to 5 years after a permit is issued, the system needs to be recertified. This can be done by a professional engineer, a third-party service, a property manager, etc. And basically, this 5-year recertification is supposed to include any type of erosion problems. Basically, you need to identify and repair any erosion problems on the site. You need to inspect and repair the stormwater control system, make sure that it's in good working condition. You have to certify that the erosion and stormwater maintenance plan for the site is being implemented as designed. And you submit that recertification form and a photo report to recert-dep@maine.gov. For more information about the 5-year recertification process, you can visit this website. This website also includes the recertification form and some information about the photo report that should be submitted. Basically, this is just to ensure that the system is functioning properly over the long term. Thank you for listening to the presentation. If you have any questions, here's my contact information. You can reach out to me with any questions. Thank you.